Alright guys, so we are moving forward in chapter 5, Thermochemistry. I'm on slide 18, and we are about to start working a bunch of math problems. So, we introduced the idea of delta H for reactions, which is an amount of heat that corresponds to the stoichiometry of the reaction. So if we look at the reaction on the slide, this is a reaction for the formation of water, where I'm taking hydrogen and oxygen to make water. Specifically, the delta H value corresponds to, it's an exothermic reaction. I know that because it's a negative value. So it tells me that this is how much heat is released. Okay, the negative tells me that it's exothermic, but then the amount tells me how much heat is released. So 483.6 kilojoules of energy are released when I make 2 moles of water, because there's a 2 in front, 2 moles of water from 2 moles of hydrogen and 1 mole of oxygen. So when those amounts of reactants react and form that amount of product, there's a very specific amount of heat that gets released. Okay? Now, what if I made 4 moles of water? Well, basically, if 2 moles of water being produced gives me this much heat, then 4 moles of water is going to be twice as much heat. So there is a relationship between the amount of heat produced and the amount of the reactants or products that get used or made. Okay, so the way I do that, I'm going to set up, I have a problem here, calculate how much heat is generated by burning 10 grams of hydrogen. So I want to go back to my mole map that we introduced before. So if you can see this, the mole map, I'm going to start with, they gave me 10 grams of hydrogen. So grams of A would be my grams of hydrogen. I'm going to go to moles, because anytime I do a chemical reaction, I always want to get to moles. And then once I have the moles of either a reactant or a product, then I can figure out whatever other thing I need. Now, one of the things I added to the mole map last chapter was a leg off of moles that goes to the kilojoules. The relationship between the moles of something and the kilojoules is going to be the delta H value. Okay? So, the way I use that, let's work through our calculation. So it's going to be 10 grams of H2. And the question asks me how much heat is released. So the heat is going to be kilojoules. Okay, now, the first step, I need to change grams to moles, divide by the molecular weight. For hydrogen, the molecular weight is just 2. You can say it's 2.02 if you want to be picky, but I'm just going to use 2. So it's 2 grams of H2 per mole. And then I can look at the reaction in the balanced equation that was shown on the PowerPoint. It was 2 moles of H2 plus 1 mole of O2 yields 2 moles of H2O. So I want to know the relationship between the moles of H2 and the kilojoules. It was, the balanced equation said 2 moles of H2 have to react, and then it will release 483.6 kilojoules. That was my delta H value. Now, notice that I left off the negative. The negative just told me that it was exothermic. If the question says how much heat is released or how much heat is generated, it's already implying that it's going to be exothermic, and it just wants the number, not necessarily the sign. It's kind of like if I go shopping and I buy a bunch of stuff, when I get home, when my wife says, "How much money did you spend?" I mean, if I check my bank account balance would go down, so that's a negative change. So when my wife asks how much money I spent, I don't say negative $100 because she knows I spent money. The fact that our bank account balance went down is obvious. The question is just how much. So when she asks me how much money I spent, I just say $100. In this question, it says how much heat is generated. I just want the amount, not the sign. Okay? So I'm leaving the negative off for that purpose because I'm just going for the amount. At this point, if I calculate, so 10 divided by 2 times 483.6, and then divided by 2 again. So I got 1209 as my value, which again, the 10 grams was given with 3 sig figs, actually 10.0 in the question. So I probably should round this to 1210 kilojoules. That's 3 sig figs, so that's probably a better answer than 1209. Okay? So again, we're using our mole map here. I didn't finish the mole map on this side, but you guys should know all that. The new thing I'm doing, I start with an amount of a sample. It could be the volume of a solution times the molarity to get the moles. You gotta remember, whatever we're given, we have to find a way to get moles. Once we get to the moles, if I'm going to another substance, I'll go from moles of A to moles of B. But if I'm going to heat, I'm gonna use the delta H value to go to the kilojoules, okay? So it's just a little side track that I can take if I need to. All right. So now I'll go to the next question, and there's gonna be the next slide. So I have a balanced equation, 2 NOs plus O2 yield 2 NO2. It gives me the delta H value of the reaction is negative 114. So now we want to talk about what happens if we change the way the reaction is written. Okay, so what if somebody wrote the balanced equation like that? Now, I know that I've told you we always balance reactions with whole numbers. There will be cases, and sometimes it's kind of a necessary thing, that sometimes we have to balance an equation with a fraction. Okay? Even though that's not the preferred way, there are times that is still correct. Okay? We'll see that later in this PowerPoint. So, if I write this reaction this way instead of the way on top, the main difference there that you should be able to see is that the bottom reaction involves half as much of everything as the top reaction. And if I'm only making half as much of the product, then it should make sense to you that it's only going to release half as much heat. So the delta H of the second reaction is going to be half the first reaction. If I make 2 moles of NO2, it'll give off 114 kilojoules. If I only make 1 mole of NO2, it'll give off 57 kilojoules. So that's an important relationship that if you ever change the coefficients, if you double them or triple them or quadruple them, or cut them in half or anything like that, whatever you do to the reaction, delta H is going to change in the same way. Okay? Now, another thing that can happen though, there are times that we can write a reaction where the top reaction is a combination reaction where the 2 NOs plus O2, they can combine to make 2 NO2s. Sometimes that reaction could happen backwards. The 2 NO2s can break apart and decompose to form O2 and 2 NOs. If you take a reaction and reverse it, which means switch the products and reactants, well, essentially on my energy diagram that we showed earlier, I was looking to see if it was still on my board. If an exothermic reaction, the reactants energy are high and the products are low, so it goes up and over. If I switch the reactants and products, it does this, and where before it was exothermic, high reactants, low products, if I swap their positions, now it's going to be an endothermic reaction. The difference between them will still be the same, okay? So, when I reverse a reaction, if that's the only change I make, just switching the reactants and products, then that's going to give me the same delta H, but change sign. Instead of negative up top, now it's going to be a positive. Okay, and those are patterns that you need to be able to recognize. So, when we do problems, we already introduced a previous problem, if you like a slide back, where if a certain amount of a reactant or a product is involved in a reaction, we should be able to figure out how much heat comes out of that reaction if we know delta H. Okay, so if delta H is given, we should be able to use it in our calculations. All right, but this next topic says, well, what if we don't know delta H? What if we have a reaction and we're trying to figure out what delta H is. Well, there are 4 different ways to find delta H. Each one kind of takes a different approach to solving the problem, okay? So on your next test, you will have at least one problem to find delta H by each of these ways. So you'll have a problem where you have to find delta H using calorimetry. You'll have a problem where you have to use delta H to find, heat of formation to find delta H. You'll have a problem where you have to use Hess's law to find delta H. And then you'll have a problem where you have to use the bond dissociation energies to find delta H, okay? So we're about to go through all these methods, but there are 4 ways to find delta H. Make sure you are comfortable with all 4 of them, okay? So we will go in order. The first one is calorimetry. If I want to find delta H of a reaction using calorimetry, that means that I'm going to go into a lab, I'm going to perform a reaction in a calorimeter, I'm going to measure how much heat comes out, and if I know how much of the reactants I used, and I know how much heat comes out, I should be able to use those numbers to find the delta H of the reaction. Okay, so the problem is on the screen. Write that information down, and I'm going to use my whiteboard. Okay, so I'm dropping 0.15 grams of sodium into 50 grams of water. Sodium is an extremely reactive metal, so they'll react right away. It's a single displacement reaction, and the reaction is given Na plus H2O yields sodium hydroxide and hydrogen. So we're trying to find delta H using the data that's collected. Okay, so calorimetry, when I drop the sodium in, it gives off heat. When it reacts, the temperature of the solution goes up. I'm going to use Q equals MC delta T. To find the Q value, and then I'm going to use Q to find delta H. Okay, now Q and delta H are similar but not the same. Q is the amount of heat that's produced in the process that's going on. So we're doing a reaction. When I find Q, that's going to relate to the amount of heat that's being produced. Okay, but Q is a random amount. Basically, if I react any amount of a sample, the amount of heat that comes out is Q. Delta H for a reaction is specific. It's the amount of heat produced when a certain number of moles react. Okay, and it has to be the moles in the balanced equation. When I react those moles, that's what the delta H value is the heat that goes with that. Okay, so we have a little bit of unit conversion we have to pay attention to. So I'm going to plug in. Q is my heat I'm solving for. My mass, 50 grams of water, but when I drop the sodium in there and it reacts and dissolves, the total mass of the solution is going to be the sum of the two. So my mass is going to be 50.15 grams. The specific heat, so it's a solution, but really it's mostly water with a little bit of other stuff in there. So anytime I'm dealing with an aqueous solution, I'm going to use 4.184 as my specific heat, unless they tell me otherwise. Okay, so 4.184 joules per gram degree Celsius. And then delta T tells me the temperature goes from 22 to 33.2. So that's a temperature change of 11.2 degrees Celsius. So that's my MC delta T. If I plug that in, 50.15 times 4.184 times 11.2 equals. That gives me 2,350 joules. So then I'd say, well, okay, that's the amount of heat produced in the reaction that I did. Delta H, though, the units of delta H are the kilojoules per mole as specified in the reaction. Okay, now that's pretty picky there, the as specified in the reaction, but we'll deal with that at the end of the problem. Okay, so I have joules, I need kilojoules per mole. So I need to change the joules to kilojoules, obviously. So I'm going to divide by 1,000 joules to 1 kilojoule. So that's going to be 2.35 kilojoules. Okay, so I'm now closer to what I need for delta H than I was before, but it needs to be the kilojoules per mole, specifically of the limiting reactant, which when I dropped in the 0.15 grams of sodium into the 50 grams of water, the sodium is going to be the limiting reactant there. So I need to know the moles of sodium. That's going to be 0.15 grams divided by the atomic weight of sodium is 23. So let me do that real quick. 0.15 divided by 23. That's 6.522 times 10 to the minus 3 moles. So I've got my kilojoules. I'm going to divide it by the moles. 6.522 times 10 to the minus 3 moles of sodium, which is my limiting reagent. So if I divide my kilojoules by my moles, that's going to give me kilojoules per mole. Okay, so let's divide that number. 2.35 divided by, so I got 360.3. I'll just call it 360 kilojoules per mole. So that looks like the answer, but I have a couple more things I need to do. Number one, this reaction gave off heat. The solution temperature went up. So I know at this point, this delta H value, the one I just found, this is delta H of the surroundings. Meaning everything I did here was for the solution. The solution absorbed heat, the temperature of the solution went up. So the delta H, or the change in heat of the solution, was positive, but the reaction gave heat off. So at some point in this problem, I have to switch from looking at the solution to looking at the system. So delta H of my reaction should be negative. And then one more thing, if I look at the balanced equation, this reaction, the delta H for this reaction should be the kilojoules per 2 moles of sodium. The reaction specifies 2 moles of sodium have to react to get the delta H value. I just found the kilojoules per mole, which means per 1 mole. If I want the kilojoules per 2 moles, then I need to double this number. So the answer is going to be negative 720 kilojoules per mole. Okay, so that's where I'm going to cut off.